Good afternoon, lads and ladies. Welcome back. Today, we have pretty much concluded all of our work with power series. There was one problem type on Wednesday that I wanted to work with you that we didn't quite have time to do, and that's kind of a cheeky, fun problem about getting information about the derivative of a function out from its power series. And well, that might seem like we're thinking backwards. Normally, when we use Taylor's theorem to find a power series, we calculate a bunch of derivatives and then try to find a pattern in those and use that to get our series. That'll be fine for Bruce, no worries. It can also be done in the other direction, where you happen to have a power series in hand, very fancy, and you use the coefficients of that series to infer about the derivatives of the function. So that's the fun thing from Wednesday that we didn't get to, that I want to get to today. The other thing I want to do today is kind of get you ready for where we're going. So the next few things that we're going to do, the last part of this class, involves looking at what are called parametric equations, or curves defined by parametric equations, and polar coordinates. Polar coordinates are a topic that hopefully you were exposed to in trigonometry. It's supposed to be a part of trig here at Santa Fe. But I think we likely need a little bit of a warm-up with both of those things before we're ready to just dive in full force. So that's the game plan for today. I won't lie, I am very low on sleep, so I'm not 100% myself here today, and I apologize if that exhibits in any hiccups here in the lecture, but hopefully we'll be all right. So this is MAC2312, section number 004, which is a Calc 2 class, and the date today is, oh, it's April Fool's Day. Well, that did not occur to me. It's April 1st, 2022. The game plan, like I said, is a cute problem with power series. And then a little intro. So we're going to start with parametric equations. So we've done an awful lot with series at this point. We spent a good deal of time developing the theory behind convergence of series. All of that was so that we could eventually talk about power series, because power series, as you've learned now, allow us to represent functions as big, long, infinite polynomials. And there's a lot of utility in that, because polynomials are easy to integrate and differentiate, where functions can be quite complicated to integrate. It was due to Taylor that we learned f of x can be written as the sum from 0 to infinity of the nth derivative of f evaluated at the center divided by n factorial times x minus a to the n. And it is a fact that power series for a given function at a specific center are unique. So in other words, if f can be expanded as a series Cn x minus a to the n, then by Taylor, the Cn's must be that fn of a over n factorial. In other words, if you have two different series representations for a function, they actually have to be the same series, as long as the center is the same. Well, what this means is that if somebody hands you a power series for some function, somebody gives you an expression like this, you can assume that the CNs, even if you have like, maybe the CN is just like 5 to the n or something, then you know that 5 to the n is the nth derivative evaluated at a over n factorial. And that will allow you to solve for the nth derivative. Okay. So I'm going to show you a kind of cute problem here, which can be solved multiple ways. One of those ways would take you many, many years. And the other one will take you just a few minutes if you think about it cleverly. Many, many years might be an exaggeration, but let's take a peek. Let f of x be x e to the negative 2x, and find, let's say, is it 2022, right? Find the 2022nd derivative of f evaluated at 0. So there's kind of two options here. First, you can compute f 2022 of x and then plug x equals 0. I claim that this is a really bad idea. This sucks. Because we have to use the product and chain rule (2022) times. Right? F 2022 is the 2022nd derivative. So you could jump in here and differentiate this once using the product and chain rule, then differentiate that again, then differentiate that again, then differentiate again, again. You're going to get really tired of using the product and chain rules. Every time you differentiate this thing, it's going to kind of get larger and larger. Differentiating it 2 or 3 times, sure, go ahead, do it by hand. Differentiating it thousands of times, I don't want to do that. I don't think you want to do that. So the better option, find the power series for f of x, and then look at the coefficient of x to the 2022. We know that the coefficient of x to the 2022 will be of this form. And this piece right here would be f 2022 of 0. This down here would be like 2022 factorial. And this will be a number that we can get because we'll have a power series. So you'll be able to straight up solve for the derivative we want algebraically, rather than computing many, many, many derivatives. So this is much better, right? This is a terrible thing to do. You do not want to differentiate that function thousands of times. I don't want to differentiate it 5 times. I would get bored after 2 or 3, and I think you would too. And more importantly, we would make mistakes. Even if we never got bored and we had all the time in the world to differentiate this thing over and over and over again, we would likely make a mistake somewhere. So we're definitely going to do this. This is much better. I'll just say it's much faster and less room for error. There's still room for error, but less. Do we understand the task? Is it clear what it is we're trying to find? And is it clear why option 2 is the better option over option 1? It's clear what it is we would have to do to go the kind of obvious path here. Okay, let's take a shot at it then. So I'm going to find a power series for f of x equals x e to the negative 2x. I'm going to use the fact that e to the u is sigma n from 0 to infinity 1 over n factorial times u to the n. Side work here. This means that e to the negative 2x is sigma n from 0 to infinity 1 over n factorial times negative 2x to the n. And I can simplify that a bit. As sigma n from 0 to infinity negative 1 to the n times 2 to the n over n factorial times x to the n. Which means that x e to the negative 2x is x times sigma n from 0 to infinity 1 to the n 2 to the n over n factorial x to the n, which is going to be sigma n from 0 to infinity negative 1 to the n 2 to the n over n factorial times x to the n plus 1. Right, just x times x to the n. We move this guy all the way in here. So my power series here is sigma n from 0 to infinity negative 1 to the n 2 to the n over n factorial times x to the n plus 1. And we know that the coefficient of x to the 2022 should be the 2022nd derivative of f at 0 over n factorial, because the series is centered at 0. So the question is, can you find the coefficient of x to the 2022 in this series? Like if you were to write out this series, what's the number in front of x to the 2022? The x to the 2022 term in our power series comes from, well, this is an x to the n plus 1. So you're going to get an x to the 2022 here when n is equal to 2021. So the coefficient is negative 1 to the 2021 times 2 to the 2021 divided by 2021 factorial. And this should be equal to f of 2022 at 0 divided by 2022 factorial. And now it's just a matter of solving for the piece that I want, which is this derivative here. So I can multiply both sides by 2022 factorial. -1 to the 2021 is just -1 because 2021 is odd. We have here 2 raised to the 2021 power at your 2021 factorial, and then I multiply over by that 2022 factorial, and that will give me f 2022 at 0. If you take 2022 factorial and you divide by 2021 factorial, this guy is the product of all positive integers less than or equal to 2022, which is 2022 times 2021 times 2020 times 2019, all the way down to 1. And this guy downstairs is the product of all the positive integers less than or equal to 2021. So that's 2021 times 2020 times 2019, all the way down to 3 times 2 times 1. So you can cancel pretty much all of those terms. You're going to get -2 raised to the 2021 times the only term that survives from the factorials is the 2022. And this is what we're looking for at 2022 at 0. It's an enormous number. Right? And you certainly would not want to get there by taking 2022 derivatives of the original function. You can get there very cleanly by using the power series. So I always like these problems. I thought they were kind of cheeky, kind of cute, in the sense that it's the opposite of what we're used to doing. We're used to using derivatives to get power series. But of course, the information is encoded, so it goes both ways. You could use power series to get information about derivatives if you wanted. And that's exactly what we did here. Let's back up just a little bit. Any questions on how we got to our power series here? Any questions on the side work we began with? Any questions on where this first bullet point comes from? The statement that the coefficient of x to the 2022 in this series should be the 2022nd derivative at 0 over, oops, sorry, it should be at 2022 factorial. And that's just Taylor's theorem. Taylor's theorem says that the coefficient of x to the n is the nth derivative evaluated at the center divided by n factorial. So the coefficient of x to the 2022 should be the 2022nd derivative evaluated at 0 divided by 2022 factorial. The tricky part here is that we're used to thinking of the nth coefficient, or the coefficient of x to the n, as being the thing you get from just plugging whatever n value in here. But you have to look at the power of x in your sum. So the power of x here is n plus 1. So to figure out what we're going to write down over here, we have to ask ourselves what value of n in this series is going to produce the term x to the 2022. Because the power of x in the series is n plus 1, the value of n that will give me x to the 2022 is not 2022, but 2021. So the series has a bunch of terms in it, and the term that has the x to the 2022 piece is the term associated with the index value n equals 2021. So if you plug n equals 2021 in here, you get this thing times x to the 2022. And we're just looking for the coefficient. So I just take this thing and I set it equal to this thing. The piece that I want is this. So when I set them equal here, I can then solve for this guy. So multiply both sides by 2022 factorial. Cancel the factorials carefully, right? Thinking of the definition of the factorial, product of numbers less than or equal to this, product of numbers less than or equal to this. And we get our answer. We can now say happily and confidently that we are done with power series. So congratulations, you've made it through what is pretty universally acknowledged as the hardest part of this class. Remember to invest time studying, studying this material for exam 3. We want to make sure that that goes as well as it can for you. The rest of the material that's going to be on exam 3 is relatively easy by comparison. I do want to go ahead and introduce that material now. So if there are no questions on this, I will move away. Are there any questions on any part of this problem? Okay. I don't want to get too far ahead of ourselves here. So we'll probably wrap up a few minutes early today, and that'll be okay. But I do want to get your brain moving in the direction of parametric equations. So this is going to be an intro to section 10.1, which is on parametric curves. The textbook calls this section curves defined by parametric equations. That's just a lot to write. Everybody that I know in the math world just calls them parametric curves. Normally, the curves we work with, the curves we sketch, are coming from functions. Stuff like y equals f of x, usually. Or maybe something like x equals f of y. And y equals f of x. And there's some limitations to what these can look like, right? Here's y as a function of x. And we have seen some curves where x is given as a function of y. You think back to the early part of the class where we were doing like volumes and stuff like that. And they look like this, right? Y is a function of x, that thing has to pass the vertical line test. If x is a function of y, then that thing has to pass the horizontal line test. But many curves pass neither many curves pass neither the horizontal nor vertical line test, meaning they can't be written as y equals f of x or x equals f of y. Circles, for example. All right, if you take a circle, you often see this as something like x squared plus y squared equals r squared. But you won't see this like y equals or x equals, because this is neither a function of x nor a function of y. Ellipses, all sorts of other things. And you could have a much more general kind of thing, like something like this. Right? Curves can get quite wonky. So is there a nice way, is the question. Is there a nice way to give explicit formulas for curves like this? Somehow using functions. And by explicit, I want to be clear what I mean. When we write like x squared plus y squared equals 1 for the unit circle, that is an implicit formula. It's not solved for x or solved for y, and it cannot be solved universally for x or for y. If you assume y is positive, then I can solve for y. If you assume x is negative, I can solve for x, stuff like that. But I can't give you like a single formula where y is a function of x or x is a function of y for the unit circle or for any circle. And, you know, more general wonky looking curves like these, they don't pass the vertical line test, so I can't write them as a function of x. And they don't pass the horizontal line test, so I can't write them as a function of y. Thankfully, the answer is yes. If we introduce a third variable, often called a parameter, t, then we can give x and y not as functions of each other, but both as functions of t. And this would be like, you know, x equals, or x of t, y equals y of t. Your book sometimes uses f of t and g of t. I think that can get confusing. We'll just call them x of t and y of t. So looking at something like this, it's definitely not true that x is a function of y or that y is a function of x, but I can think of both x and y as functions of a third variable that doesn't show up anywhere in the graph, which we call t. In other words, I can think of this curve as being the path that is traced by a particle or a little ant walking around in the plane as the variable t goes from some value to some other value, say 0 to 1. So at time t equals 0, my little ant is over here. And as t goes from 0 to 1, my little ant crawls around here. If I want to know a point on the graph, I can just plug in any t value to both of these equations, and that will give me a specific x value and a specific y value, which is a point on the curve, a point in the plane. So I'm going to give you some terminology, and we'll look at an example or two. So these are called parametric equations. they're going to play a medium-sized role in the remainder of the course here. They're going to play a huge role in Calc 3. And of course, in physics, if you ever take a physics class, we often parameterize motion with respect to time. So x will have its own function, and that will be a function of t. Y will have its own function, that will be a function of t. And we'll usually specify a range of t values, say a is less than or equal to t is less than or equal to b. The curves here can be quite general. There are some names associated with specific points on the curve, and there's this concept of orientation. So I'm just going to draw a very sort of general looking curve here. Like I said, usually we think of this as a motion. We think of it as a particle moving around in the plane. The point over here, which we call the initial point, has an x value and a y value. The x value is what you get by plugging the starting t value into the x function. The y value is what you get by plugging the starting t value into the y function. This is called the initial point. And then as t increases, we are moving along the curve. A general point on the curve just looks like x of t comma y of t. And when you get to the end of this curve, when you get to t equals b, you would be at the point x of b comma y of b, which we call the terminal point. The little arrows I've drawn going along the curve from the initial point to the terminal point indicate what's called the orientation. So parametric curves have this feature called orientation, meaning that you start somewhere and you walk in a particular direction along the curve, right? I could start over here and walk this way along the curve. But by calling this the initial point and this the terminal point, I'm inducing a particular orientation, saying I'm going to start here and walk this direction along the curve. And when you sketch parametric curves, which is the first task that will be set to you in 10.1, you always want to draw and label all three of these things. Draw and label the initial point, draw and label the terminal point, and draw and label the arrows that indicate the orientation. We're going to learn how to do calculus with these curves. Meaning we're going to find tangent lines. We're going to find mins and maxes wherever possible. We're going to talk about how to find areas. And then we're going to find a couple other cool things called arc length, which is like if this curve were a piece of rope and you were to like lay it out flat, how long would it be? And we're going to talk about something called surface area, which is related to the volume calculations we did at the beginning of the class. But before we even try to do some calculus with these, I want to sketch a few specific ones. Okay. So I'm giving us a set of parametric equations. Here's the function x of t. Here's the function y of t. And I'm told t is going to go from -1 to 2. These two things together should give me a curve, right? So, something like this with an initial point, a terminal point, a curve connecting them in orientation. Think of it like you're going back to middle school or elementary school. If you want to sketch the graph of something, you make a table. Well, let's make a table. Let's do it. I'm going to manifest my table here with 3 columns. T, X, and Y. T is what we call the independent variable. And here both X and Y are dependent variables. And for T values, I'll put -1, 0, 1, and 2. I'm going to leave some space in there if I want to insert some like in between T values later. When T is -1, X is -1 minus 1, which is -2, and Y is -1 squared, which is +1. This tells me that the point, my initial point, is the point -2, 1. When T is equal to 0, X of T is 0 minus 1 is -1, and Y of T is 0 squared, which is 0. So this means another point on the graph is -1, 0, right? X is -1, Y is 0. That's a point. When T is equal to 1, X is 0, and Y is equal to 1 squared, which is 1. So I have this point 0, 1 on the graph. And when T is equal to 2, X of T is 2 minus 1 is 1, and Y of T is 2 squared, which is 4. And this would be my terminal point. One, 4. So basically, I've got some points on the graph. Let's plot those points. I'll mark, let's say, -2, -1, 1, 2. We go 1, 2, 3, 4. I know my initial point is the point -2, 1. It's right here. I've got now the point -1, 0. That's right here. And this is my x-axis. This is my y-axis. So -1, 0 is right here. The point 0, 1. And the point 1, 4. So if I connect these with a curve, again, thinking just how you would in, 8th grade, there's your graph. The initial point is this -2, 1. The terminal point, this point 1, 4. And the orientation would be like this. So these parametric equations, x of t equals t minus 1 and y of t equals t squared, gives me this graph. Oh God. I just drank like the dregs of my coffee cup. Oh, that's bad. Oh, it's like drinking sand. Whew. Okay. Questions about how we're getting this graph by making a table? Let's try another. Let's sketch a parametric curve. Given by x of t equals 2 times the cosine of t, and y of t equals the sine of t, where let's say 0 is less than or equal to t is less than or equal to 2 pi. Again, without any other tools, all we can really do is make a table. My t values here are going to be things that I plug into trig functions. So I should pick nice numbers for t, numbers that are kind of nice to plug into trig functions. And they have to come from this interval 0 to 2 pi. So I could plug in like 0, maybe pi over 2, pi, 3 pi over 2, and 2 pi. So when t is 0, x of 0 is 2 times the cosine of 0, which is 2 times 1, or just 2. And y is the sine of 0, which is 0. So we're starting here at the point 2 comma 0. When t is equal to pi over 2, x is 2 times the cosine of pi over 2, which is 2 times 0, which is 0. And y is the sine of pi over 2, which is 1. When t is equal to pi, x of t is 2 times the cosine of pi, which is 2 times negative 1, which is negative 2. And y would be the sine of pi, which is 0. When t is 3 pi over 2, x would be 2 times the cosine of 3 pi over 2. Cos of 3 pi over 2 is 0. And the sine of 3 pi over 2 is negative 1. So this would be 0 and negative 1. At 2 pi, cosine is equal to 1 again, so this is 2, and sine is equal to 0 again, so this is 0. So the curve we're looking at here, x values appear to go from negative 2 to 2, so it goes 1, 2, negative 2, y values run from negative 1 to 1. And our initial point here is 2 comma 0. Then we have the point 0 comma 1. Then the point negative 2 comma 0. So it looks like we're doing something like this. This. And the orientation arrows would go like so. We're starting over here, and as t increases, we go over there. As we run past t equals pi, we come here towards this point, 0 comma negative 1. And then as t goes back towards 2 pi, we're going to come back over here. This is the point associated with t equals pi over 2. This is the point associated with t equals pi. This is the point associated with t equals 3 pi over 2. And our terminal point is the same one, same as the initial point. So the idea is just this. For every t value, you get an x and a y separately. But then that x value and that y value tells you a point on the curve. And if you string together all those points, you get the whole curve. Questions about where this graph comes from? Okay, there are kind of two other things I want to talk about here. First, relating to this problem. The curve above is an ellipse. All right, it's like a stretched out circle. So any parametric equations of the form, you can imagine how to modify this, like x of t equals a cos t, y of t equals b sine t, will give you an ellipse. Centered at the origin. With vertices coming from these numbers a and b, right? A comma 0, 0 comma b, negative a, 0, and 0 comma negative b. The equation of an ellipse in regular xy stuff, right? If you're okay with the implicit kind of we call it conic equation, is x squared over a squared plus y squared over b squared equals 1. That's considerably more complicated than like a cos t and b sine t. So this gives us a much nicer way of writing ellipses. And since a circle is just an ellipse where the semi-major and semi-minor axes are of equal length, another little note here, if a and b are equal, we get a circle. So this gives us a way of writing circles and ellipses in parametric form. In other words, we say we can parametrize the circle or parametrize the ellipse. The other thing I want to introduce today, and then after this I will let you go, is how do you go back and forth the normal equation for this ellipse, or for the, we didn't say it, but this thing is a parabola. It's not the whole parabola, it's part of the parabola. Or for the parabola from the previous example. And the answer is something called eliminating the parameter. So I'm going to do it for the parabola first, because I think it's a little bit simpler. And then we'll do it for the ellipse here. So what I want to do is find, like, this thing is a parabola, or it's a segment of a parabola, right? The parabola continues forever and ever over here, forever and ever over here. If I want to find the normal, like, xy equation, we can eliminate the parameter from x of t equals t minus 1 and y of t equals t squared to get a typical xy equation for the parabola. If your parametric equations are kind of nice, simple equations, algebra or polynomial type equations, then the easiest way to eliminate the parameter solve one of the equations for t. And plug that expression in for t in the other equation. Those are your steps to eliminate the parameter. If your parametric equations involve trig functions, then solving one of the equations for t is generally not the move. You'll want to use some trig identities, and that's why we're going to look at the other example also. But here, I had x equals t minus 1. I'm just not writing the of t. And y equals t squared. So if I take this first equation, I can solve it for t really easily. This is the same as saying x plus 1 equals t. That's my like step 1. So y, which is t squared, should be x plus 1 squared, i.e. this is the curve y equals x plus 1 quantity squared. Now, our parametric curve is a portion of the parabola y equals x plus 1 quantity squared, which is how to graph that. You take the regular x squared parabola and you translate it over, right? Which portion is it? Well, you want to find the x values on here that correspond to the time domain, the t values we were given. So the t values we were given were -1 less than or equal to t less, or sorry, -2 less than or equal to t less than or equal to 1. So to see which part, find the x values which correspond to -2 less than or equal to t less than or equal to 1. When t is -2, x is -2 minus 1. Was it from, did I go -1 to 2 or 2? -2 to 1. Negative. We did -1 to 2. Sorry. Should be -1, positive 2, positive 2, positive 7. So when t is equal to -1, x was -1 minus 1, which is -2. And when t was equal to positive 2, x is equal to positive 2 minus 1, which is positive 1. So that tells me that my x values are going to run from -2 over to positive 1. Right? Something like this. So that's the portion of this parabola that my parametric curves represent. This can provide an alternate path to graphing these things. You can eliminate the parameter to get a regular xy equation, which is the sort of thing we have more experience with, and then find the x values that correspond to the prescribed t values. I'm going to go ahead and do this for our ellipse, and then I will let you guys go. Questions about how to eliminate the parameter in parametric equations? Okay. So, last example for the day. Eliminate the parameter in our parametric ellipse. X of t equals 2 cos t, y of t equals sine of t, where 0 is less than or equal to 2 is less than or equal to 2 pi. The trick when your parametric equations are trigonometric, especially sine and cosine, is going to be to use the identity sine squared t plus cos squared t equals 1. So I know that x is 2 cos t, which means that x over 2 is equal to cosine of t. I want to use this identity, so I need a cos squared. So let me square both sides. And then I'm going to do the same thing with the y's. Y is just sine of t. And I know I need sine squared. So I square both sides and I get y squared is equal to sine squared of t. Now, since I know sine squared t plus cos squared t is equal to 1, we get that y squared plus x squared over 4 is equal to 1. And this is your standard form of an ellipse. So our curve is an ellipse. Right? X squared over a squared plus y squared over b squared equals 1, with a squared equal to 4. So a, your semi-major axis length is 2, and b squared is equal to 1. So the length of the semi-minor axis b would just be 1. these, like everything else in this class, will take a bit of getting used to. So if you finish up the homework before next Monday, I invite you to crack open the textbook and peruse section 10.1. What we're going to do when we come back is work through more problems in 10.1, lots of sketching parametric curves and this stuff. It's a lot of fun. The trick to getting comfy is to just look at a shitload of examples. These can get quite complicated. We'll work through the cycloid, which is a classic problem. It's very nice. And then we're going to look at how to do calculus in the context of parametric curves. So how to find tangent lines, how to find areas, how to find all sorts of good stuff. Especially exciting for this will be the concept of arc length. And arc length, for those of you who are going to go into anything related to what's called differential geometry, problems in physics related to general relativity, we'll see a lot of utility down the road. Certainly GR is not the only place where differential geometry is important. It's just the first one that comes to mind for me. After talking about arc length, we'll talk about surface areas. And that's going to be pretty much our whole week next week, is just playing around with parametric curves. And then the very last thing we're going to do in this class is learn about polar coordinates, which is something that you should have seen back in trigonometry. But if you didn't get to that in your trig class, or if you're rusty on this, you might want to watch a YouTube video or two over the next week to kind of prep you for this. Because we're going to move quickly. I'll go back through the basics that you should have learned in trig for polar coordinates. And then we're going to do some calculus with polar coordinates. And that will be the end of the class. So you're almost there. You're almost to the end. If you have anything that you're dying to talk to me about, you can come see me in an office hour today from 1 to 2 p.m. or you can send me a Canvas message or an email. Otherwise, I will see you guys on Monday. And I just want to say again, please work that homework, stay caught up, practice the power series stuff. Exam 3 is not going to be that hard. The 10.1 through 10.4, all of this stuff is not that bad. The challenging stuff on exam 1 is the power series stuff. So make sure you're putting in an appropriate amount of time practicing that. Make sure you can like come here to chapter 11, grab a random problem from 11.10 or 11.9 and solve them correctly the first time without help. If you can do that, you're in great shape. And that is definitely the best way to kind of try to prepare yourself for exam 3. That's it from me, guys. I will see you on Monday of next week. Have a fun and safe weekend.